recording working. Yes.
So we started recording. Peter?
Hey folks, can you hear me?
Yes.
Sorry, can I sneak to the front of the line real quick?
Yes, please do.
Can you, this is Alvaro, by the way, Jeff, can you repeat what you said at the very beginning so it ends up in the recording?
Sure. So we're about to start interim meeting with IETF routing working group dedicated to routing in data centers. We are starting with folks who own design data center networking. We're going to talk about problems they're facing, maybe potential solutions from their perspective, followed by folks who are proposing solutions as extensions to different routing protocols or possibly new routing protocols. So first person to start is Peter Lopakov from Facebook. Thank you, Peter.
Yeah, sure, no problem. The slides you have right now are supposed to be Rift. Okay, there you go. So should I ask you to advance the slides?
Yes, please do, sir.
Okay, so folks, I'm Peter, network engineer at Facebook. I have probably 15 minutes to describe very briefly our key challenges in data center. So let's get started. Jeff, can you do the next slide? So I'll start by just giving you some terminology that we use often. It's pretty common, just maybe some terms could be different from company to company. So data center network, as you can imagine, usually has a bunch of top-of-rack switches, right? Rack is a building unit. We have top-of-rack that usually aggregates 40 servers, could be more, could be less in some cases. This is the open rack specification. In our new design that we deploy pretty much everywhere, we usually assemble multiple racks in a pod. It's a physical term. Usually we have 48 racks maximum in a pod. Could be more in some cases, could be less. Multiple pods could be assembled into a cluster. Oh, different slide, Jeff?
I'm sorry, I'm trying to mute everybody.
Oh, okay. I'll hold for a sec.
Besides you, actually.
I think you muted me, actually.
I can hear you. Oh.
Okay, I just muted myself.
That's great. Okay,
so we were at the slide which had pod and cluster. So cluster is assembly of multiple pods. It's a logical term. Cluster usually have like one large subnet, V6 or V4, and that's used by logical planning. And fabric is the assembly of the hundreds of pods in data center. So fabric reflects a whole building, physical building, the full network, which is, in our case, is class topology. It's very common these days, right? Everyone has it. So class, I think we have blog post on this. It's public. It has like 4 planes, usual design. So you have 4 fabric switches in every pod, and then they fan out to like 48 spine switches and so on and so forth. So next slide, please. So the way topology aggregates is starting from pod, then to fabric, and to region. So we have multiple regions, let's say Oregon, West Virginia, Luleå in Sweden. Every region usually have multiple buildings, and each building has its own fabric. And between buildings, you have yet another aggregation layer, what they call regional aggregation. And so this is usually like from 8 to 16 large switches that assemble all the fiber, single mode fiber from all the buildings and connect those buildings to the WAN network. So these guys connect to, let's say, classical WAN routers and provide cross-data center traffic. So the reason I highlight this level, the cross-building aggregation, is because traffic growth there is probably the fastest. As I'll discuss later, we have this situation of traffic non-locality. We have lots of traffic crossing between buildings because applications tend to be placed in such a way that people tend to disregard the locality of the placement. Next slide. Okay, so real quick, next please. Speeds and feeds, it's pretty common, you know, nothing new. You have servers, it's a mix, 10G, 25G, 50G mix. Still lots of 10G servers. We carry infrastructure with trunks are usually 40G or 100G. So we're in this period of transition from 40G to 100G. Lots of links are still 40 now in data center. All new deployments are now 100G on single node. And definitely there's like interest in moving to 400G. But right now, let's say for the next year, will be mostly on 100G technology, I would think. Okay, next please. So application mix at Facebook is interesting with classical stuff with storage. So you have machines that are at storage level, let's say HBase or Hadoop. You have compute machines that pull from your storage. So this creates interesting traffic non-locality when you have traffic from some pods crossing across the spine and going to different pods. So there's very intense flows between some pods. It's interesting because quite a lot of traffic leaves the pod, right? So you would assume that traffic will stay inside one pod, but very often traffic is going across the spine and crossing the data center backbone to reach to the other pods. We have a mix of applications. So most important ones is probably one of them is caching. So Facebook does use cache infrastructure extensively inside data centers and at the edge and pretty much everywhere. So you have lots of machines that serve pretty much data from memory or from flash, right? So this creates, in some cases, I won't say pervasively, in some cases, the problem when you have in cascade type behavior on fabric switches where we pull data from multiple machines from memory, and this creates very large traffic bursts. Next slide. So our subscription, though usually in a class, it's super expensive to build fully non-blocking fabric. Usually we all subscribe at the rack switch, right? Say you have 40 servers, say for example 10G, could actually be different, 50G, and you have like 400G uplinks, right? Or 800G uplinks. So main point of subscription is at the rack layer. Pods have 4 fabric switches. This is a place where you can actually tune our subscription. Usually it starts with like lower number of links, let's say 12 uplinks, and you can add more and more and go to say full non-blocking bandwidth as demand grows. And this is done for like cost optimization purposes. We start like building from say of subscription 2 to 1, and slowly growing to 1 to 1 of subscription at the pod layer. In some cases, we just build fully non-blocking fabric. If say we know a data center will have say lots of storage or Hadoop clusters. So once again, cross data center layer is the one that assembles together multiple buildings. This is where traffic grows very, very fast. And this is where we have most of our subscription. So this is where we usually have like large boxes. So we can quickly add more capacity as demand grows. This is a place where we actually have to manage the density because fiber between buildings is more expensive than fiber inside buildings, right? So you have to speed it up, add more ports, add more links on demand. WAN and data center, as I mentioned, this cross-DC aggregation layer attaches all buildings. It serves a front layer to the WAN network, long-haul network. This is where you have easier to plan capacity because you know how much traffic leaves data center. So you can provision as many ports on the WAN side as you want. The key here is like, okay, managing these ports because they are once again more expensive than the counterparts on data center side. So this is where you have to be very careful, just not to over provision, well, just to maintain things sane. Okay, next slide, please. So probably people always ask about utilization. I think you have a paper, a SIGCOMM paper from maybe last year that analyzes traffic patterns with Facebook. At a very high level, there are hotspots at some racks, let's say there are storage racks or cache racks that occasionally get overheated. Majority of racks are actually pretty cold. It's like most of the racks don't push that much traffic. We do see high utilization in pods that say contain the warm the storage clusters, say Hadoop storage or other forms of storage, because these guys have to serve traffic across the data center spine. This is where we usually have to be more proactive and add more capacity, but on average, the utilization is reasonably low because most of the applications don't generate much traffic, right? Well, last but not least is that cross-DC utilization is the fastest growing. This is the one where we have to be much more, say, reactive and have capacity in place to quickly compensate for traffic growth. It's interesting, but most of the traffic primarily grows in data center. Traffic across the WAN is more stable. It's primary replication traffic, say for caches and data centers. And of course, the traffic going to the users, which is also like more predictable because it has nice trend line and we can easily forecast its capacity. Okay, next slide, please. So I mentioned the microburst and incast patterns. Used to be very, very common 5 years ago on 1G networks. As we move to 10G, almost all of them are gone because synchronization becomes less problematic to create between applications. We do see sometimes high discard rates on the pod switches, so called fabric switches, when you have, say, multiple racks sending traffic to one rack. This sometimes creates buffer pressure. Not very frequently. I'll probably seen this happening maybe like a few times a year. And it's usually specific to an application, let's say the app that sends lots of data from memory, which creates lots of buffer pressure for short periods of time. And usually we alleviate this by talking to people, hey guys, can you like desynchronize the flows? And usually this kind of goes away pretty quickly. So it used to be a big topic, right, in the past, microbursts and incast. Nowadays, it's probably not a problem we've seen very often, so that's quite the interesting change. Next slide, please. So routing, okay, routing, this is why we're here, right? So let's look at the next slide. As you can imagine, the primary goal when we built the fabric was to keep it stable, operationally stable is my main primary goal. Programmability was interesting, mostly to divert traffic to different bits, so you can do injection and move traffic between machines or load share using Anycast. Our use case was also very IPv6 heavy, so we had to invest a lot in testing the 6 routing and the 6 feed capabilities. Was also progress in the past with feed and hardware implementation for IPv6. And last option that we actively, I'd say, focus on today is being able to try new things quickly when we need to, right? So being able to react fast to changing environment is probably specific to Facebook. Like typically cloud companies like in before, they focus on efficiency, like cost, operations. They don't think, okay, can we build a network such that we can easily change parameters or topology or protocols, right? This is what probably is quite different at Facebook because of thinking, is keeping this opportunity to innovate. So next slide, please. So right now it's all BGP, right? BGP is pretty common thing these days. It's stable once you test it well on multiple platforms. We have multiple BGP implementations from multiple vendors, right? Our own on MPOS. A few other vendors that we use right now also have their own. So we took some time to test it. I think the key difference from what we described in RFC once is that Facebook does summarization at pod layer. So we send the 6 and the 4 summary routes from every pod. The main reason for this was in the past to maintain the feed table size manageable, because in the past we have, say, Broadcom silicon, which can only accommodate, say, 4,000 prefixes, right? So this was a problem. These days, it's not an issue anymore. With the Trident 2 and Tomahawk, you have LPM, right, lookups, but we still maintain summarization, mostly for stability purposes. Because I would say in the past, I've seen at least 2 cases when the flat BGP network was destabilized because of like there was no boundaries or delineations or any kind of route summarization. So Facebook also has a pretty intense BGP prefix policy on every session, mostly for security reasons. Okay, security in terms of fault propagation. So you can contain precisely where prefix goes and what happens with prefix, such that, say, people cannot inject something that can propagate to the whole data center. Like a few cases in the past in some companies when you
Pager, can you hold on a second? There's an over caller who's actually, is everyone else hearing calling user 24 with news?
Oh, I can just hear the speaker.
No.
It sounds pretty good.
Okay, call-in user 20.
I hear it. It would be good if it was muted.
Could you please mute call-in user 24? It's completely impossible to hear for me. Someone's putting a newscast in here. Thank you. That's wonderful. I'm sorry to interrupt you, Peter. It's just that I actually want to hear what you're saying.
No worries. Okay.
And it's back. Somebody please mute call-in user 24.
24 just dropped, I think.
Ali, does it sound okay now? I don't hear anything besides.
No, I'm still getting it. I don't know where I'm getting it. I'm gonna have to drop off. I'll be right back.
Okay.
Okay, Jeff, can I continue?
Let's give it 20 more seconds, please.
Okay.
Let's continue.
Okay. So since you have a summarization, you need some tricks to avoid black holing, right, on link failures. So definitely had to implement some logic to be able to use like rec switches to bypass the failed links in case of link failures. This works surprisingly well. It does add some complexity in the configs, but it's been tried and been working, I would say, for 2 years now. So BGP overall has proven to be very stable and easy to operate if you don't change much things. And you can imagine data center things are very, very static. The only thing that changes is, say, VIP injection. The host may inject the prefixes, mostly for load balancer purposes, and then this is probably the only thing that changes. And it's interesting, these VIP injections create constant churn because people often remove and re-inject them. If you enable BGP monitoring, which we actually have on every switch, you can see how often we propagate in the topology. And anycast, let's say VIPs, is probably the only source of churn in the network because they propagate pretty much in the whole, say, data center or cluster. Next slide.
So Peter, this is AC. You don't use Anycast?
AC, we wait with questions till Peter finishes. Please hold off.
Oh, okay. Well, yeah, I hope that I'll finish shortly. So as you can imagine, I think we've been told this multiple times, V6 is primary source of traffic. I would say 99% of traffic inside V6 now. V4 is still kept for just in case, you know. Although most new clusters have only V6 enabled on the servers, we still have V4 sessions just in case. Because infrastructure just reuses the same IP address space for all the sessions. It doesn't consume any resources. We invest a lot of efforts in tooling that works with BGP, say mostly drain and drain. Graceful restart, say to work with FBOSS, because say when FBOSS upgrades, you simply restart BGP process. And graceful restart was really helpful, right? You can kill BGP on rec switch, restart it, it comes back, nothing, no disruptions, nothing happens. It's kind of critical for a rec switch to support graceful restart because we do FBOSS roles very frequently. I would say probably every 2 weeks you have to push it to the whole fleet, and maintaining this graceful restart was a critical piece of functionality. With BGP, we noticed these days very low packet loss on the convergence. Used to be problematic, mostly because of ECMP implementation in many vendor hardware, excuse me, was not very optimal. Let's say people used to say grow ECMP groups slowly incrementally, which caused like traffic to hit few links very heavily and cause congestion as ECMP group shrinks or expands. These days people optimize this a lot. So there were some tricks we used to work on FBOSS and with our vendors to make sure they can program ECMP more efficiently. Say you wait for full span out to arrive before you program ECMP group. You cannot program say 1, then 2, then 3, because this causes you like this heavy hit on a few member links. So next slide, please.
Peter, 5 minutes.
Yes, almost there. As I mentioned, stability and simplicity was definitely operational goals. Innovation is the new thing that we definitely trying to push forward. Innovation means make network in a way that you can change things easily, right? Change protocols, change features, and so on and so forth. So next slide. I think almost there. So OpenR, I think you heard about it. This is what we deploy right now in data center. At the same time, it's still like deployments aren't that large because we try to be much more careful. People don't like breaking things. Simulations show we can run this very easily on large scale, but OpenR is kind of the answer to this innovation dilemma, being able to change things quickly, like in our own way, without depending like on the vendors, right? That's kind of the key idea of OpenR, being able to control the routing stack on your own. Next slide, please. Okay, a few things about FBOSS. So FBOSS definitely is becoming the dominant system in data centers. Next slide, please. This creates a few interesting caveats, right? So right now with Broadcom, we definitely explored our chips. We have Wedge and Backpack, two main platforms. So Wedge is like single chip, a top of rack switch. Backpack is a multi-chip chassis. But the thing about Backpack, it has multiple ASICs inside, and every ASIC has its own CPU, let's say, associated with it. So Backpack looks like, say, 12 routers. So right now, if you use OpenR or BGP, you will see this as a 12 individual units. And as you replace, let's say, the other switches in the data center with the Backpack, the number of routers and routing instances grows significantly. Let's say if you have 100 switches, right, and you put in Backpack, you have now 1,200 switches instead. Next slide, please. Once again, inside, say, a Backpack, you have right now OpenR and BGP facing outside, right? But the key challenge is multi-chip topology. It's right now it's not as large, but I think within the year we'll reach the scale. We'll probably start hitting the problems with having so many routing instances in one box, right? That's probably, from browsing perspective, is the most interesting aspect, because right now, let's say using BGP, you can definitely hide stuff inside the box by doing summarization. With OpenR, you definitely expose the guts of a box out as a link state topology. There are tricks to manage this, but right now we're still exploring all these options. Next slide, I think this is the last one. That's it. As I mentioned, innovation is a key goal, and I would say, to be honest, we are now on CLOS. CLOS works really well. We still want to be able to use any topology if we have to, because CLOS has one problem. It's totally great for load balancing, load sharing. The only challenge is capacity growth, like density. It has lots of chips, lots of wires. And as you move to 400G ASICs, potentially we may hit a problem when you see the power increasing, right? Power usage per network gets higher and higher. And so people start thinking, hey, can you optimize this topology, pack it more efficiently, and use less power? So bulk operations are mostly referred to the way when you work on a fabric, we usually treat this as a single unit. So you have tools that allow you to bulk upgrades to the topology, configs, and devices. Say, drain a whole plane in a floss topology, or shut down a bunch of links. And having this CLI and tools is also critical for operations. I think that's it. Next slide, just to be sure.
Yes, that's it.
Okay, great.
Thank you very much,
so
Peter.
That's our final stage. Thank you.
Yeah, so now we've got some time for questions. So to be clear, we cannot answer all the questions, so the intention is to initiate email threads on every presentation. So I see you are the first. Please go ahead.
Okay, I got a question. Are you pretty much, with your BGP implementation, still in line with RFC 7938, where you peer on the local interfaces and do heavy ECMP pretty?
Oh yeah, BGP is the same as we have with the RFC. I would say the difference there is majorly in the way that Facebook has route summarization, right, and the pods. And the RFC was like, oh, route summarization is kind of tricky. It definitely is tricky. There are ways to manage it, and there are trade-offs. But Facebook decide, okay, we want to focus on stability and summarization and add this functionality. Everything else is pretty much following the same logic. There are tweaks and caveats, of course, optimizations, but it's all eBGP pretty much on the physical IP addresses of every link.
Okay, and the second question is, how did you say you were using Anycast? You're not using Anycast with UCI?
Okay. So let's say you have layer 4 load balance.
Guys, please mute. Someone is broadcasting something.
Let's say you have a full load balancers like VoiceTP. All these folks announce the same IP address, right, or same IP prefix, more likely. In our case, they attract traffic. So network does load balancing. The first page, you have, say, 16 hosts in different racks. You fan out to these hosts, and then they perform load balancing on these flows. So Anycast is typically used for service discovery. Let's say when you bootstrap data center, you have to bootstrap, say, chef hosts and tell DNS machines. And second one is that load sharing, right? Initial stage of load sharing, which is two main use cases in data center.
Oh, I got one final question.
Yep.
What's the average number of routes in your top layer spine?
So if you talk about cross data center, I would say right now we've been testing it to the scale of up to 64,000, I think. But typically it's just on the order of like 20,000 prefixes right now. And even less, like maybe less than 20,000. And it's a lot of this contributes from VIPs, right? There's lots of VIP injections and they propagate to the upper layer aggregation tier. But we always purposely test all these boxes to be able to handle 64K prefixes before the 6.
Okay, I'll let others ask questions. Very good presentation.
Thank you.
I have a question. So Peter, when you have these disaggregated backpack routers that are basically 6 routers in one, so today I assume you're running each one of them as a BGP speaker. Is this sort of how you see this going forward, or are you trying to optimize?
Oh yeah, so right now it's very straightforward. You have IBGP inside, eBGP outside. This is cross design, right? Inside you have these 4 spine chips which use as out reflectors, for example. Right now we have the option when you have OpenR inside and say a full mesh of IBGP sessions and then eBGP outside. It's very classical IGP and BGP sandwich, right? With another scheme, we have only OpenR across outside of the box. In this case, you can see the link state topology of the box in the outside world. In the production deployment, right now it's eBGP and IBGP inside. We explored the option to have that MPLS inside. For now, we decided not to do it because it just adds more operational complexities. So inside the backpack, you have like this IP switching, IP routing, basically working.
Okay.
So if no more questions, we will pass to the next presenter.
Cool, thank you.
Thank you, Peter. Appreciate your time.
No problem.
So next presenter is Dmitry Afanasyev from Yandex. Thank you, Dmitry, for presenting, and please go ahead.
Hi, can you hear me?
Yes, I can hear you well.
Yes, real good.
Good. So my name is Dmitry Afanasyev. I'm a network architect for Yandex, and well, I'll try to recap what we have now and how we evolve to the current state of our data center network, mostly data center. Also, I will mention a bit about other parts of the network and what kind of problems we've seen during transition and what we see in the future. Next slide, please. Well, we are a rather typical organization which builds massively scalable data centers, maybe not as massively scalable as some other companies, but still they're quite large. So we're serving around 90 million users. Now, after that, services is a typical mix with search, music, cloud storage, whatever. And some of them are producing rather typical loads. So, and we have, for infrastructure, we have several data centers in Russia and abroad, plus peering points and MPLS backbones to connect them. Actually, not one backbone, but 2, which is rather typical. One is for interactive traffic, and another one is for bulk traffic. Our workloads are of course, user-facing, it's interactive request processing, and on the back side, it's object storage, it's MapReduce-like workloads, data streaming and message queues, rather large ones. It's large-scale replication. You can imagine that we are building search index on some computational clusters, and after that we need to replicate it, and it could be quite fancy replication because different portions of the user index are replicated different number of times on different subset of machines. And also machine learning, which can produce rather big traffic spikes. Next slide, please. So basically what we wanted and what we currently need, we want a lot of bandwidth, and that bandwidth shouldn't heavily depend on location. So we definitely want full bandwidth in cluster, and if possible, we want full bandwidth in data center campus, and of course, due to the costs of wide area links, we still want a lot of bandwidth between data centers, but we are not aiming for full bandwidth there. Still, we want to build scalable forwarding, but keep minimal state in the network if possible. For historical reasons, we need also network virtualization or VPNs, because historically different large groups inside the organization were building more or less isolated computational clusters or application infrastructure, and they just assumed that there will be some sort of filtering or isolation between them. So in terms of address space, they're using normal global IPv6 address space, but they still assume some amount of isolation, and we have to keep it for a while. We also, of course, want efficient resource pooling, and that means that there is daily migration of workloads to and from machines, because there are daily variations in, for example, search workloads. To efficiently utilize what we have between data centers, we want traffic engineering at least between data centers. And we want stable routing system, of course, but at the same time, we want reasonably fast converters. Not something like telco people sometimes want, but still we'd like to converge in several seconds and probably a little bit sub-second if possible. Also, for processing external requests, we need what essentially is service chaining, because requests come, we need to load balance them, we need to apply some filtering or catch some malicious traffic. Essentially, it's a service chaining, so we need to implement it. And last but not least, we need to automate all that. Next slide, please. I think very essential part is also to be explicit what we don't want to do. And what we are not doing and don't want to is to do any layer 2 connectivity. But if nodes or applications really want it, they can implement it themselves using overlays. But as an infrastructure team, we don't support overlays, we don't provide them. But of course, we don't prohibit them. We also don't support virtual machine mobility, because our applications are, most of them are homegrown and developed internally. They are typical scale-out applications. They don't care about nodes coming and going, and we really don't need to take the state of the node and move it to some place. It's more easy to just instantiate a new process or new node and attach it to the existing cluster. Another thing which we don't use is multicast. Until recently, we did have some applications which were using multicast, and largest of them were using something between 2 or 3 gigabits of multicast. So that's quite a lot, but currently we are using data streaming or message queuing for that, and we don't use any form of multi-hop multicast. Of course, we're using link local multicast. And we don't really have, based on statistics, too many changes in topology, especially changes which are additions. Nodes, network nodes, they cannot appear out from the blue sky. It's usually provisioned. Of course, failures happens asynchronously, and so that means we have rather few additive changes to the topology, and of course we have quite a bit more subtractive changes in the topology when something goes down. But if there is a baseline provisioned state, how network should be, it's quite stable. Next slide, please. So what we have at the moment, we have quite a bit more at the moment than 100K servers, and that number is growing. We are mostly like 99% IPv6 internally because we started transition to V6 many years ago. But of course, we still need to serve external IPv4 traffic, and most external IP traffic is IPv4, and so we have to use tunnels to deliver it across infrastructure. We have two separate ones for interactive and bulk traffics. Our population of servers is currently, at least what we've been deployed for the recent 2 years, it's 10 gig to the servers mostly. Inside the data centers for switch-to-switch interconnects, it's 100 gig for recent deployments. We also have a few N by 40 gig, and on one it's usually N by 100 gig. It's lambda size up to 200 gigs. We're also looking at 25 gig to the server, but current impression is that it might be useful with some applications and in some places, but most workloads don't need that much sustained bandwidth. Over recent years, we eliminated layer 2 in new data center designs, and currently we extended layer 3 to the top of the rack. And since we also have to support network virtualization, we either extended VPNs, MPLS VPNs to the top of the rack, or at least we are extending multi-VRF. In this case, we need to support VPNs on the next layer in the fabric. And we're also trying smaller layer 3 domains, something like layer 3 per switch port, and even extending layer 3 to the server, which is useful if we are doing virtualization of the server. We eliminated multi-hop multicasts, and we're currently using /64 prefixes per server, which is good for virtualization. And another useful property is that it removes most neighbor discovery traffic from top of the rack switches. And we had a few local meltdowns because of ND, because we had some applications with very good memory, which remembered that there was some virtualized instances in that prefix, and they were keeping sending traffic. And since nodes were removed and switch couldn't send traffic there, a lot of neighbor discovery processing happened on top of the rack switches. We can be sure that entire /64 prefix is beyond that attached machine and will be processed internally. We remove almost all neighbor discovery processing from the Tor, and that's quite useful for stability. Also, for historical reason and at some kind of technical depth, we are using internal firewalls. And since we are implementing closed topologies, there's a lot of use. Yeah. Okay. Should I continue?
Yes, please do so.
Okay. So we still need to implement some filtering, and when we have a lot of multipass, it's the only logical place where it can be implemented efficiently is the host. So we are moving to the host-based firewalls. And to improve scalability of that filters, we are also doing some tricks with host part of IPv6 address. Basically, we are allocating 32 bits to encode the project to which particular instance belongs. Project is some sort of large group inside the company with their own applications and part of resources. So next slide, please. What our infrastructure needs to support is 10K plus clusters. I mean the single computational cluster instance. So in terms of how many machines some cluster headends are controlling. For membership, it could be larger, but for computing over the largest currently available data sets, we need up to 10-something thousand nodes. And our recent DC designs scaled to something like 25, 30K nodes. We are building closed fabrics with 2 spine layers. Most new deployments are with modular spine switches, but we are also looking at fixed configuration boxes, and we have at least one pilot implementation. But to build sufficiently large fabric with fixed boxes and still have only 2 spine layers, we need 64 or more ports on fixed configuration switch. And some vendors are promising some such switching chipsets in the near future. And we had a lot of discussions internally besides using module switches for spines or fixed configuration switches, and there are a lot of properties which we like about fixed switches. Basically, you have one routing protocol instance per one switching entity. If it comes down, it comes down. If it's alive, it's alive, and we getting rid of a lot of synchronization issues which we have in typical modular box. At the same time, we quite like the idea to put several routers into the same chassis with common ventilation and power, but still for them to behave as separate entities. That's what Facebook guys are doing. So we like that idea, but in this case, each individual chipset is essentially exposed to the topology. We can see that they're separate, and most savings are in terms of power and ventilation and using internal connectors instead of cabling, which is quite useful. In terms of scale, we are essentially announcing just a few prefixes per top of the rack switch, so it's between 1K and 4K eCMP routes in one DC, and eCMP could be between 4 to 16 way wide, and if we will use 64 port switches, we expect that eCMP can be 36 way wide. In terms of data center size, one of realistic limits is how much power is available in single place. Because 30K nodes is it's quite a lot, and realistically, one of the serious limitations is power, and that's why we are thinking that 64 radix switches will be enough for most implementation, because with 64 radix we can build something like 2000 top of the rack switches fabric, and if we add the third layer, then realistic limitation really will be power, because it will get beyond 150 megawatts. We don't have that much in single place.
Due to 5 minutes.
Yeah. Another serious limitation is the size of eCMP tables, because on, for example, Broadcom's chipset recently, they had a decent forwarding table size, unless you are using eCMP. But ECMP-related tables were much smaller. And if you want to extend MPLS to the top of the rack switches, there is one more problem, because with IPv4 or IPv6, you can essentially rewrite entries for all the next hops. But for MPLS in generic implementation, you need separate rewrite entry for each next hop. You can't reuse them. But this problem can be alleviated using global labels and some internal optimizations, like special operation for swap label to the same. It doesn't need any external modifications to the protocols, whatever. It's just internal optimization on the switch, and we think it's useful optimization in case we need to extend MPLS to the top of the rack switch. Next slide, please. In terms of control plane, we are using BGP in data center fabrics, and we are actually using two different flavors. One is something very similar to RFC 7938, but not with external BGP, but with internal BGP, and essentially each spine switch is routing reflector for lower level, and each doing next hop self. Otherwise, it's similar to RFC 7938. One of the reasons was that we didn't want to maintain additional namespace for autonomous systems. And since configurations are generated automatically, it's not a problem, really. There are some additional keywords in configuration, but it's not a problem at all. And another design which we are using is also with iBGP, but we are using separate softboxes which serve as off-path route servers. The reason is that we built a few fabrics using modular routers, and later found out that they don't work, they are not very stable when they have hundreds of BGP sessions. And large module box has a large fan out to the top of the rack switches, and we have something like 200 something, for example, top of the rack switches attached. And we found out that even with a small number of prefixes in each BGP session, sometimes those boxes are not stable just because they don't have a lot of BGP sessions. So it's a workaround essentially. In wide area networks, we are using OSPF with traffic engineering, and one of the main reasons for that is that we do need traffic engineering in wide area networks. Topology there is not as regular as in DC fabrics. And in future, we are really considering using segment routing with TV there. Another observation is that when we bring more bandwidth into the data centers, instead of DC borders, which were like 2 routers per DC or 4 routers per DC, DC border is starting to look like a small fabric. So it's a lot less bandwidth than in DC fabric, but a lot more routing information. Routing tables are much larger. So it's a special kind of small fabric with large forwarding state. Next slide, please. And the last one, essentially. What we see is challenges and with where we had problems. Big challenges are with diagnostics, measurements, and monitoring, because we have most problems or least understanding with the fast processes and some transient events, something like buffering, incast, convergence, and how they correlate. Another problem is how to balance between reducing control traffic and routing information in forwarding state, and still propagate enough information to achieve granular traffic manipulation, like traffic drain when removing nodes, traffic steering, or traffic engineering. And how to quickly adjust load balancing in presence of failures. Because for that, even in fast topologies, we have to look beyond single hop. With basic BGP deployment, we essentially see only some computed update from the next hop, but we don't have any visibility into what happens beyond that. And if we don't have intact closed fabric, but closed fabric with some failures, sometimes it's useful to be able to see beyond single hop. And another thing is, which we are doing, but a lot of things can be improved, is combining programmability and centralized control with local reaction to events, mostly to failures. BGP is a good tool here because we can build some softbox which externally looks just like BGP routing reflector from the protocol point of view, but it can do much more interesting logic inside. So that's it.
Thank you, Dmitry. Guys, questions?
I have a quick one. I saw you said that a problem with the Tor
Hey, please introduce yourself.
Oh, AC Lind Cisco Systems. Dmitry, I saw you said on the Tors you had a limitation with MPLS, but you might be able to get an ECMP, but you might get around it with something like global labels and segment routing. Is that a goal of yours to do that, to extend MPLS all the way to the Tor and steer traffic end to end?
In fact, we extended. We have that in very small deployments, experimental deployments. We'd like to do that in the data centers, and we are deploying hardware which is essentially capable of that, but software is not quite there.
Okay,
and just one note: some old chipsets just cannot optimize that ECMP for MPLS. You also need some support in hardware, but protocols are fine. Okay.
Okay, if no more questions are there, we'll move to LinkedIn. Sean, Ross, please get ready.
Okay, and while you're making that transition, this is Chris here. I have a procedural issue in that we need to produce a virtual blue sheet with the attendees for this virtual meeting. We captured the participant list on the WebEx. However, since several people have signed in with either just a first name or initials, if you signed in with a name that isn't, recognizable as, your full name, send an email to Jeff and I at rtgwgchairs@ietf.org. The same applies to people who have called in because we can't identify them with just call-in user numbers. So send us that email so we can include you in the final Blue Sheet attendee list for this virtual interim. Thanks.
All right. Hey guys, this is Sean Zandy. I'm here with LinkedIn for about 5 years. We've gone through a lot of in our infrastructure. Can you guys hear me?
Sean, the quality is not so good. Could you please try to get closer to the mic?
Absolutely. And I know we have only 10 to 15 minutes. Let me see if I can mute one.
You just disappeared.
All right. Sorry about that. So can we move to the next slide? The first one doesn't have any content.
Cannot hear you.
Next slide, Jeff. I don't know what's going on. Sean, you coming back on? Are you okay?
He just left the meeting.
Oh, maybe he's dialing back in.
Russ, would you want to start?
Yeah, I guess I could. This is really his section, but that's fine. All right. So LinkedIn, what we're doing is we are doing a single SKU data center, what we call a single SKU data center. We're trying to deploy essentially the same box. Oh, you back, Sean? Anyway, we're trying to deploy essentially trying to deploy the same box everywhere. It's a 3.2 terabit switching capacity Broadcom based. These boxes are used in a spine and leaf to build up 4 separate fabrics, as you can see there in the diagram. Anytime you want to take over, Sean, just let me know.
Sure. Quality better now?
Yes, much better.
Yes, it does.
Okay. Sorry about that, guys. I had to reconnect. So, and I pass it over to you, Russ, so we can do a teamwork here. Our infrastructure is pretty simple now. We use the same switch, same SKU everywhere, in top of the rack, leaf, and spine. We have 3 tiers. That's why we call it, 5-stage class. We want to have minimum latency and deterministic amount of chipset that goes, for every packet from east to west. However, this simplicity and, reducing our hardware footprint to only one single SKU and one single software creates some complexity in terms of number of links, glasses, fiber optic. Our minimum number of links to start and build a data center is around 32,000 links. So it adds a lot of, complexity to the control plane. Next slide, please. So we can, quickly pass this one. Since we are not using a chassis, it opens all the internals, and we can, have a dedicated control plane per chipset. Next one, please. So our existing, currently we are using BGP as this is the only control plane option, which is a standard and is interoperable between vendors as well. We use 4-byte ASN, no summarization anywhere, every RUS is visible in every device. We use separate AS number at every point. And the simple thing that BGP does is just, supporting the scale, sending reachability information, and using different AS number to prevent loops and provide hop count routing. We do not use any special attribute extensively. However, due to BGP, our memory footprint in every switch is a little bit larger than what we expected. Next one. So Russ, you can talk about this, what we are thinking about the control plane and where we're going.
Okay, on the control plane side, what we're doing is we're working through the process of building our own control plane for this fabric. Some of the requirements that we have right now, this is not all of our requirements. Of course, we have some other ones that are not directly routing related, but are rather more operationally or net-eng related. So fast, simple distributed control plane. We're not going towards a pure kind of centralized SDN play. That's not really our goal in the long term. Our goal is more think about where you should distribute things and where you should centralize things and try to put them together in a way that makes sense rather than distributing or centralizing everything. No tags, no bells, no whistles, no hacks, no policy. Policy tends to, such as traffic engineering and stuff, inbuilt inside the control plane itself. The control plane, the distributed control plane anyway, should really be focused. What we're working on is focusing that on just reachability and topology information and not policy information. So I just said a second ago, we're thinking about what we distribute and what we've centralized. What we're thinking about centralizing is primarily policy, which is like filtering and dragging things into, like if you see a DDoS attack or you see an internal attack or an internal traffic flow that looks weird and you want to drag that into some place for further inspection and stuff like that, that's all policy, and we're trying to get that out of the control plane in its native state and make that more of an overlay centralized type function. Of course, we have auto discovery of neighbors and building the rib and stuff like that. Primarily from an actual rack and stack perspective, what we're trying to get to is NetInge or NetOps should be able to take the box, remembering this is a single SKU. We don't have chassis boxes, things like this. Should be able to take the box, take the switch out of the shipping box, rack it, stack it, plug stuff into it, and turn it on, and maybe configure something like a loopback interface or a router ID or something, and that's pretty much it on the entire box, and everything else should just work. Of course, we want to be able to use TLVs for future extensibility, backward compatibility, things like this. So we're looking at things that are only TLV based, and our only kind of requirement is MPLS labels. We're not talking about doing MPLS-TE in the kind of traditional sense. We're thinking more in terms of some variant of segment routing, primarily for all the policy and stuff like that. So that's kind of where we're going. The one thing we do want to be able to do is if the NetInge guy or NetInge person configures a router ID, let's say, and an MPLS label, set of MPLS labels that this box can use, we want those to be advertisable through the distributed control plane. So next slide. Some of the things we're looking at BGP. These are some positive and negatives for those. Like BGP seems like it has a lot of weight, a lot of features and stuff we don't need. A lot of modifications to support the type of configuration environment we're talking about. One kind of interesting thing about BGP is without something like BGPLS, you don't get a full topology view of your entire network, and that's kind of important. If we're going to abstract out policy in some way, we want the controller or the policy engine or whatever you want to call this silly thing to be able to see the full topology. But the good thing about BGP is it does provide proven scaling. We're looking at IS-to-IS as well, possibly. Of course, IS-to-IS people will jump up and down and tell you can't scale it in this environment. I don't know that I agree, but that's one thing we're facing. It's very lightweight. Most of our requirements for zero configuration are already met, and it provides us with a full topology view. We're looking at doing something like what Petter's doing with OpenR, building something new. There's a lot of work involved in this. Could use bits and pieces from other places. So these are kind of the things we're looking at right now that we're considering as far as control planes go. Next slide. You want to do this part, Sean?
Sure. Obviously, one of the problems that we have is ECMP is not deterministic. Hop by hop, you can have different results. For some applications, such as storage, we would need to have better control over the network. And sometimes, application owner or operator want to move the flow from one set of links to another for testing or for any troubleshooting or improved performance if needed. And these things, do not exist obviously right now. So some sort of end-to-end as opposed to hop-by-hop forwarding would be ideal. Next one, please. So one of the problems that happens time to time is because we have these 4 parallel fabrics that they're not connected to each other, but they're only connected at the edge to cabinets. Forwarding happens regardless of how much traffic is that fabric is handling or where the congestion is, because everything looks equal. And extending some form of segment routing and having centralized view for a specific application can help us to deliver packets in a better way for a specific application, not necessarily for 100% of our needs. Next one, please. So the other thing Russ talked about, how other configuration is important for us. One of the pain points that we have, and we could, scale our builds much faster. We need another network to create a network, and that is our out-of-band system. So first of all, we need to bring an out-of-band network and then connect devices to that out-of-band and configure stuff to start forwarding. If you could, make network just work with connecting wires and start forwarding and then doing additional configuration or tweaking if needed, that would be beneficial. And I think that's it for us.
Thank you. Sean and Ross, questions, please.
What is BMC?
Jacob, please introduce yourself.
Oh, Jacob Heights, Cisco Systems. What is BMC?
So BMC is basically a chipset with a firmware that you can, and we have it on servers as well, that if you lose connectivity to the operating system on a switch, you still have a way to connect to there and do imaging and, a parallel way of accessing devices. Facebook has opened the BMC initiative that you can Google.
Thank you.
Okay, more questions.
Sean?
AC?
This is AC Lynn of Cisco Systems. Do you advertise your link addresses or only minimal? I mean, I see you don't do any filtering or summarization.
Right. We don't do any summarization, and we do not advertise our link addresses. Actually, we are doing BGP. We are working on BGP peering on link local addresses, not even global addresses. Those are not necessary. However, each server, participate in any cast domain, so we're going to have a lot of /32s and /64s in IPv6.
Okay. Does that present any management challenges by not advertising the each endpoint?
Well, of course, it breaks, at some aspects of trace route and those kind of things. However, these days we don't really use trace route that much because it doesn't show much. There are so many.
Then you're going to use RFC 5549.
Correct.
For dual stack with the link local address. Okay, great.
I've got some questions with regards to fast failure detection. Do you envision control plane to be fast enough to notify you, or you would still require some lightweight protocol like BFD to run between end devices?
Right now, we're still thinking BFD as far as I know, Jeff.
Thank you.
More questions, Nikolai Mikhailov, Ericsson. To all three presenters, do you need large buffers in your case, like larger than Tomahawk can do, more than 16 megabytes per NPU? And the second question, do you need wire speed recirculation, like NPU should do double lookup without any performance degradation and without any internal loopback? Thanks.
So in terms of buffering, I think 16 meg is enough for us. We rather, with drop packets if they are not being, forwarded in a timely fashion than keeping it. However, this is something that is still studying. We don't have almost any other option anyway. I missed the second question. Sorry.
Second question in chat, and it is regarding wire speed recirculation on the NPU. When NPU can do double layer 3 lookup without any performance degradation, and it can do without internal loopback.
Right now, we don't need any recirculation on the NPU, but if we decide to deploy any kind of tunneling in the future, that will be preferable to be able to do it wire speed.
Hi, one question. This is Uma Chandure from Huawei Technologies. So, do you often see the linker node failures, or node failure is important for you guys, or how is it?
Well, it really depends on node, right? Because we are single Tor. If a node fails, the whole cabinet goes offline. The application, however, should be resilient enough to survive. In terms of node failure in the spine or somewhere in transit, I think our RIP can handle it, pretty quickly with alternate routes, so that shouldn't be a problem.
Hi, this is Anasis Kiperlis from JBIL. Can you expand on the last bullet? Why do you need an out-of-band network for bring up? Why can't you do it in band?
Well, when devices are, racked in the, it's a very long story. There are certain things that need to be configured beforehand in order to bring the whole, forwarding up. I can write up the process in detail and send it to the group.
That would be amazing. So if no other questions.
Actually, it's Dmitry Afanasyev, Yandex. I have a question. You mentioned that you are using linked local addresses for peering sessions. Does it mean that you are using eBGP or you are somehow doing that with iBGP? Because we really like to use linked local, but unfortunately there is no standard way to do that with iBGP at the moment.
Right. We are not using any iBGP. We use separate AS numbers. So yeah, it's happening with eBGP.
Okay. Thanks.
Okay. Thank you very much for your presentation. And we are moving to the solution part. So we are about to start with Cure. Please get ready. Cure?
Morning, guys. Morning, guys. Can you hear me?
Yes, I can hear you.
Super. Thank you. Good morning, guys. My name is Keyur Patel, and I'm going to talk about BGP-based SPF. This is the extension that we have done to BGP protocol. Next slide, please. So we presented this this draft about 2 IETFs back, and we've gone a interesting response on the draft. The main motivation behind doing this draft was that the massively scaled data centers today, as we have seen, has implemented some kind of a simplified layer 3 routing. For the operational simplicity, most of these MSDCs, as we now know, 3 of them had presented already before me, have converged on BGP or of flavors of BGP. And for the centralized route control purpose, they've been using some kind of a controller-based architecture. Next slide, please. So a route controller, in some sense, has a functionality that is fairly similar to route reflector, in sense that it may reflect routes, and it may act as a central database for policy enforcement and management and whatnot. However, a subtle difference with route controller is that whenever you compare it with route reflectors typically assume a presence of IGP protocol to help resolve non-connected BGP next stops. In MSDCs, this problem is typically solved by having a in-band peering session between leaves and spine. And what that results into is that the next stops are pretty much one hop away. They're almost directly connected or resolved over a directly connected links. This solution that we are presenting helps deployment of controllers where you could have a peering with the controllers and thereby preserve the operational simplicity and yet get the non-directed or non-directly connected next stops to resolve. Next slide, please. So some advantages of SPF over traditional distance vector. If you run some kind of SPF or a flavor of an SPF, because you will typically have complete view of topology for the fact that you're doing Dijkstra and not a distance vector. Only network
here, I'm sorry to interrupt you. Guys, could you please mute? You are disturbing the presentation. Okay, please continue.
Thank you. Only network failures need to be advertised, and there is no head of line blocking for the fact that you don't need to do best path and then re-announce it out. So it's a much faster convergence and a much better algorithm from scaling standpoint. Furthermore, it lends itself to optimal path selection in any route reflector like controller-based topology if it is present in the network. Next slide, please. Now, the advantages of doing SPF along with something like BGP is that we've heard before most of the deployed base in MSDC today uses flavors of BGP. It's fairly robust and a scalable protocol. It has wide acceptance, as we know. The transport is fairly reliable, so you're not going to lose the packets. There is inherent optimization built in delivering packets. It's guaranteed in-order delivery. It can do incremental route updates. It can do incremental updates upon any session restart, so the protocol has been completely optimized from that point of view. You don't need to flood. You can do selective filtering. You can apply policies, and it lends itself to multiple peering models depending on what the operators would want. Next slide, please. Furthermore, when you start to deploy some sort of controllers or have some kind of a control point inside a closed network, the big advantage of using such a solution is that you have a control point inside a network, be that be a separate, so be the control, in either case where a controller resides in a cloud or it coexists with spines. In either case, the solution works seamlessly. You don't have to go about doing any in-band peering sessions. This kind of an extension can be used for all the underlay SAFI that a clause would deploy, and it would give a much better convergence. The overlay SAFIs could still use the underlay SAFI, and the overlay SAFIs could still go about doing the best path according to the BGP manner. And for the fact that you have a controller in the network, you could do any end-to-end traffic engineering very easily. You could orchestrate a path and inject it within your network, and all those things could be doable. Next slide, please. All right, so I'm going to talk about a solution a little bit. If you're going to do some kind of SPF inside BGP, then you need a notion of link state packets. That has already been done inside BGP outside this extension as part of an RFC which is called as BGP-LS. So we have defined a new SAFI here as part of this solution. However, the packet format of the new SAFI leverages the packet format of BGP-LS. We could make this extension very easily over BGP, existing BGP-LS SAFI. We chose not to do it so that we don't muddle LS SAFI in any ways, but we could very easily eliminate SAFI if need be. For the fact that we have a capability because of a new SAFI, we can indicate that each and every router is capable of executing Dijkstra. Again, lends itself to a multiple peering model, and due to the fact that we have capability, we can now signal two routers to effectively remove the vector algorithm and replace it with Dijkstra fairly easily as part of the decision process. Next slide, please. Now, if you're going to run Dijkstra, then technically the next hop attribute that you carry within a BGP update becomes pretty much a no-op, because each and every hop will compute its own next hop as part of the extra. But we are going to keep it so that we don't violate RFC 4271. Essentially, as part of this draft, we replace decision process phase 1 and 2 by just executing SPF algorithm. And this decision process 3, which is the part of the route announcement, would be short-circuited since the NLRI is unique. By that, I mean you don't have to run SPF and then announce the updates out. You could do the announcement in parallel, and that actually helps towards convergence. And we've also tried to leverage that the most recent version of the updates we receive in BGP always gets announced by the fact that the existing protocol mechanisms guarantee that. Next slide, please. So the SPF itself that we are running is fairly simplified. We basically run with single area to begin with. Scales very well. It can easily be extended to support computation of LFAs, segment routing stage, any other IGP features. For the fact that we are running SPF, we support dual stack for V4 and V6. The packet formats in LS already supports that, so multiple chassis is not a problem. Any work that is needed is to define an interaction between a underlay and a overlay address family. If there is any, how do you basically recurse and resolve the next stops of an overlay address family over this address family as opposed to a traditional IPv4? Any of that work that is needed is a matter of local implementation and can be done outside the bounds of standardization. Next slide, please. Like I said, any peering models can be supported. You can have a controller or a route reflector-ish that supports this extension to reside on a spine or on a separate network. You need to do some kind of a link level liveness and discovery if you're running something like this to make sure that the links are up and running. And that is outside BGP. There are existing link discovery and liveness mechanisms that could be leveraged very easily here. The controller could learn the topology from LS. SPF is fairly distributed. It would run and be executed on each and every router. And if you look at this model, it's very, very similar to Jupiterizing the clause part that Google earlier tried to do or has executed at some point, with a difference that it is done with a standardized protocol. Next slide. Yep, that's about it. Questions?
So if no questions, we'll move to the next presentation. Naming. Dan, are you ready to present?
Yes. Can you hear me?
Yes, I can hear you well.
Okay. This slide deck is evolved from iSize draft, which is a spine leaf extension. Although I have to point out we have not published the version 3 yet, but in this slide there's additional information comparing to the previous version. Next. In this deck, I'm going to talk about a general use case and the basics of this extension and the TLVs. And in specific, I'm going to talk about the clause case link and node down treatment and give a summary. Next. Next. So spine leaf is very popular. Next. Normally, the leaves have to go to one of the spines to reach another leaf in the east-west. And it's basically ECMP. Leaves are ECMP to all the spine nodes. Next. And this rich mesh of spine leaf, in case, I mean, I'm talking about the IGP is used here in the data center, and creates also massive flooding issues for the LSLAs and the LSPs in the event, in particular, when the link and the node failure. Next. So this is a basic drawing of an example, and we are talking about at the bottom there is an access layer which is a leaf nodes, and on the top there is an aggregation layer which is the spine. Next. And we assume on the aggregation layer we have the normal I-size operations unchanged. Next. And on the connection between the spine and the leaf, this is the extension which is new. And from leaf, it will announce a new option which says, I am the leaf. Next. And the spine nodes will use hello to advertise I'm a spine, and you can use me as a default route. Next. And so in this particular case, and let's say leaf 3. Leaf 3 receives 2 spines an advertisement through the I-size hellos, and it knows it can reach both of them, and it's doing the load sharing for the default routes. Next. And in this particular case, we can also have another layer on top of the aggregation layer, which is typical. People call it a core layer, and it's between the pods and between the data centers and also exit to the WAN sites. And also that portion can be used for rerouting if it's possible. Next. So this is the basic TLVs, and we define a new TLV. This TLV, which described in the new draft, can be used in the hello or the circuit scoped flooding scoped LSP. And so the AL bit is to indicate I am the leaf, and the R bit is indicates I'm the spine. Now, let's just skip here for the B bit, which is between the leaves for the local traffic inter-exchange. And also, if the spine wants to have impacts on the normal ECMP, and it can use the I-size reverse metric to inject a different metric for the leaf nodes, and to do an unequal cost load sharing in the case of congestion or overloaded condition on the spine nodes or links. And optionally, in this new draft, we include several sub-TLVs. One is called a leaf set, and one is called an info request. and another is IPv4 and IPv6 info advertise. Next. And in this particular case, I'm drawing a typical clause topology, which has two layers, three layers, access and spines and the core layer. Next. And we assume that above the spine layer, above the aggregation layer, we are running normal I-size IGP. And it can be multi-layer, multi-levels, like the bottom two layers running level 1 and the top two running level 2, you know, we can scale out like this. Next. And basically between the spine and the leaf, it's as described before. And the leaf can set the L bit to indicate it's a leaf. And the spine can set the spine bit and also advertise a set of leaf it connected to. So this is new. So let's say S1 will advertise I can reach L1, L2, and L3 in this case. Next. Okay, next. So in this take example, let's say we have some prefixes connected to L6. They can be the loopback of L6, P1, P2, and a P3. And we have a switch wants to go over there, and the switch on the L4, for example, only connects to the spine nodes S3 and S4. So they're load sharing in the default route. Next. Let's say the L4 picks the S3 as the gateway to reach the L6 for the prefix of P3. Next. In this particular case, we are considering an example of that particular link is down, which will stop the traffic we just seen. S3 to L6 is down. Next. And the S3 leaf sets will send the information saying, I actually only have the leaf sets of L4 and L5. But S4 certainly still broadcast, I'm connected to L4, L5, and L6. Next. So in this particular case, L4, for example, send a request inside the sub-TLV called info request sub-TLV saying, hey, forward me the prefixes behind this node L6. Next. And in this particular case, S4 use, let's say, incremental SPF or something, or it stores already in the database. It says, hey, L6 I have connection to, right? And my policy says I can advertise P1 and P3 for you. So it sends you can reach L6 to P1 and P3 through this info advertised by the S4, because S4 was requested on that information on this lost L6 node. Next. And L4 in turn learns this thing and will install a more specific prefix on the routing table and the forwarding table saying P3 and P1, I can use S4 to reach them. Rest of them still the same. It's a default route. Next. So this is how the reroute works in the link down case. Next. In the case of a node down, this is a leave node down. I mean, S1 and S2 were both saying we lost L3 in their leave set advertisements. There's nothing we need to do. Next. And in the case of node down of a spine node, same thing. There's nothing happen, nothing you can do, and the default route will obviously only points to S1 in this case. So in this particular case, when we are solving the massive flooding problem, in particular, a node down causing a lot of previous flooding issues, in this particular treatment, a node down has zero flooding. There's no flooding at all. Next. So to summarize this, next. So the leave nodes in this particular extension has no topology at all to all the other nodes except nodes all about its own directly connected spine nodes, and the SPF is not even needed. Next. And this rich connectivity of spine leaf topology does not cause any IGP flooding issues. Next. And if topology has interconnections among the spine nodes, like horizontal connections, as the first picture I'm showing, or if there is a core layer connectivities, the reroute can be utilized by those connections in the case of the link and node down. Next. But for pure clause, without the core layer, or even you have the core layer, you have the horizontal connections possibly, but sometimes you want to guarantee the traffic latency and all those issues. You don't want to go through those extra hops reroutes. And in this particular case, negative routing, which I'm talking about, I actually lost the connection to this particular node advertisement. And or in the overlay terminology, they call conversational learning. So you don't have to have all the information. When you need it, you can gain this by some little conversation. But in the overlay conversation, usually is data-driven. This is a topology change event-driven conversation, can be utilized to learn specific prefixes. Next. And so this proposal basically is proposing a thin underlayer to work with overlay or BGP in the routing and forwarding in the data center. I think that's all. Next. Yeah, okay.
Thank you. Please, questions?
Naming?
Yes.
This is AC again. So you added that fourth bullet. That's the part that's not in the current draft, right?
Correct. The pure clause conversational handling is in the new draft. Yeah.
To give the optimal path even in the event of failure. Okay.
Right.
I think that's a good addition.
And I'm talking about I size, right? But I mean, all IGP is similar, right? So.
Any other questions? Thank you, Naomi. Tony,
Thank you.
please get ready.
Okay, now did I click on all the buttons? You guys hear me?
Yes, I can hear you.
Okay, so good now. So put up the first, please. One back. So hi everyone, good morning, at least my time. Tony P. from Juniper, and I would like to present something we worked on for a while, which is basically a modern protocol that we intend to build for the DC topology requirements. We call it RIFT, catchy, routing in fat trees. So it's really fat trees of clause variations. Next one, please. All right, so why is the big question. Why in couple senses? The primary, of course, why would you build something new, right, rather than patching things with all the stuff that we did for the last 20 years, which I was a good part of. Next one, please. So the why is best answered by looking at the requirement metrics that has been distilled over the last 4 or 5 years when data centers really started to grow big and hit all the problems. It's largely 7938, which is Peter's BGP for data centers, plus about 6 or 7 additional requirements that we see from different sites. Ideas that people have vary. Some want distributed planes, some are really in love with controllers. SR is coming in. So we looked at the proposed extensions, what they can do. We looked what people really want to do, and then from what people really want to do, we kind of did the math and came to the conclusion that it is significantly simpler to build something new, which is purposely built towards the requirements rather than go about patching around the other protocols. I'll go through the requirements. Some of them are not on, which we widely agree with, like, for example, what Peter mentioned, that we need very fast innovation cycles here. And we all know that the protocols built in the last 20 years are fairly hard to move. So let's look what needs to be done. So what we observed that people are concerned about, the link discovery, so the switch is coming up auto, and coming up in a sense that they don't do cabling violation on the topologies, because when unexpected nodes talk to each other, all kind of havoc ensues. So BGP has no session detection that can be, of course, added. I mean, anything can be added to anything. This is at the end just software. And ISIS can do it to a certain extent. So we saw the attempt by naming, like, having the leaf detection and so on. But ultimately, we are talking about 3, 5 stages folded clauses. We may go to 7. Who knows where the whole thing will take us. So the detection becomes its own problem in a sense of nodes coming up in the right pods at the right levels. Minimal amount of routing information on TORs. So neither the BGP solution in generic sense, eBTP flat, right? If we talk aggregation, we run into the other problems we'll talk later. Nor ISIS is maintaining minimal amount of information. We saw these leaf extensions, right? So we built something which maintains the minimal amount of information on every level of the fabric. Now, whether this is important is, of course, arguable, because people have different perception of what memory and CPU cost. But if we agree that because this whole thing at the bottom gets very wide and the bottom nodes become, a lot of them having huge requirements drives the cost up, it is probably a good thing to maintain the minimal amount of information at every level. The next one is the high degree of ECMP. And here, we're not even talking ECMP. What we're seeing is that basically people want to saturate the fabric in an optimal sense. So they want non-equal cost ECMP, weighted ECMP over time. So BGP can do that at a certain cost because you have to carry the path through all the parallel links, or you go towards a controller that computes the stuff offline. ISIS can do it, of course, very well. Link state protocols are very good at ECMP. The traffic engineering. So I think this is one of the requirements that really drove the BGP from bottom up, because link state protocols simply not built towards policy, except on the edges where they basically become a distance vector protocol. So we wanted something that has a property that you can employ traffic engineering on it by prefix injection, or basically sloshing the right amount of prefixes based on policies across the fabric. Whereas we don't preclude, injection by control or anything like that. The other problem where ISIS or any kind of IGP is very good at is, seeing all the links in the topology to do things like a PC or SR computation, which are becoming a requirement. We see that there are attempts in BGP to somehow find out the link state for faster convergence, but also, driven by the requirements, things like BGP-LS to do computation across the topology. The thing that I think Facebook suggested, which is an intriguing idea that a lot of people respond to positively, is that people would ideally like a key value store, some limited size right after the protocol converts, so they can actually bring up functionality of the node without running another level of convergence. For ISIS, it's doable. Right, we have opaque data. It just takes a good amount of time to bring anything like that to standards. For BGP, it is a fairly hard problem because unless you change the path selection and don't really run BGP anymore, because you have to retain all the copies, whereas you're really only interested in the best copy of the key value store, whatever we consider the best copy. Of course, you can build extension that if you lose the best copy, you can request the second best and so on, but then BGP starts to move, more and more towards an IGP solution. The other requirements that we see is that people want to take nodes out of production very quickly and without disruption. So for ISIS, we have overload bit, and that is fairly easily done, right, for IGPs. For BGP, this presents an interesting problem in the sense that you really have to withdraw the routes, and even if you withdrew them, you don't know how far upstream they made, so you may be still hammered and black holing traffic. So here, again, this is something that drove our requirements, and we pretty much copied the overload bit solution. Automatic disaggregation. So that Peter pointed out that Facebook is putting a lot of aggregates together. That's really how you scale up. On link failures, this thing can start to black hole or backhaul through your spine. So no one really attacked the automatic disaggregation on failures. We went all the way and can basically, on the Rift solution, we can automatically disaggregate the minimum amount of prefixes necessary while we still preserve the maximum ECMP through the traffic. The minimal blast radius, so here some footsie work has been done as well by the other solutions. So it is really mildly vesting in the sense that if you start to restrict your blast radius, you may have a hard time on failures or on exceptions. If you make everything flat, so you have all the information everywhere, anything shaking will shake your whole network. So we have a solution which actually does the minimal amount of shaking necessary to reconverge the fabric in every case. The fastest possible convergence, that's mildly contentious. IGPs are, by the nature of the algorithm, which is a distributed rather than a diffuse computation, limited just by the propagation delay of the link state. So they will always have a lag up. And it is admitted that you can make a BGP that converge very fast. Vendors are around that can be done. If we start to talk going through route reflectors and such things, with every hop introduced and every translation like BGP-LS introduced, of course, you will pay a penalty. Good. The last one is, and that is still high on the list of many people, and that is admitted, that BGP obviously presents a much simpler implementation initially, until you start to add all the knobs on top of it. So that is unavoidable. Link state protocols or flavors of link state protocols do have a price that you have to pay upfront. All right, so that's kind of the requirements matrix, something to ponder about. That's also in the draft, pretty much laid out. If people disagree, want to discuss that, very welcome, especially, you know, customers building fabrics at different sizes. So having gone through that stuff, which is kind of the meat, what drove us, we can talk about the how, and I will not go into much detail. The draft is there, and people skilled in the hardware understand how the stuff is put together. I just give it 10,000 feet overview. I don't know whether it's a claim, someone using the bell, or just, you know, like. All right.
Just go with it.
It's a whole bell or something. All right, so from 10,000 feet down, this thing is put together from really 3 pieces, and it looks pretty different from anything that has been done before, except it will remind you of a lot of things that has been done before in parts. So after we kind of looked at the stuff from the bottom up, you know, driven by the requirements, we realized over time, having worked, you know, towards either distance vector or link state modifications, that what a fabric, and I'm drawing here a clause, but we can also talk about, you know, the clauses with partitioned fabrics at the top, you know, the super spines, that all works, is that what you need is really a link state going up, because the super spines need all the information, not only to make the right decision routing-wise, but also to provide information base to do things like PC or SR computations or any kind of centralized computations. So the controller can pretty much hook up to those guys to get all the information at any given point in time.
Tony, sorry for interruption. Do you want me to move slides?
No. Oh, sorry. Yeah, I have my own set. Yes, please flip the slide forward. I forgot that I have to tell you. All right, so I'm at point 1. So I'm showing, you know, red, green, blue fabric. The red layer does not have to be a perfect clause. It can be partitioned fabric, can be butterfly. All this stuff works. So what I said is that when we looked at the requirements and started to fiddle with the link state and the distance vector, we ultimately came to the conclusion that you know, the math, the necessity of which information needs to be where, preconditions a different approach. And the approach is, so that's the point 1 on the right, is that we do a link state flooding up. So the super spines have a link state, flat topology. And that allows to attach things like a controller that needs the full view. And it also is necessary to make the optimal routing solution in terms of going left or right at the very top. So it's unavoidable. Now, I'm not saying whether we carry individual addresses, prefixes, whatever it is basically link state with the attached prefix. While when you go down, you actually want to condense information. So the point 2 to the very left is that going down, you really run a distance vector protocol. So in the most extreme form, imagine that you are just giving default routes down. And that is absolutely sufficient. At the very bottom, the blue nodes on the left basically just have default routes and ECMP over default routes, or non-equal cost ECMP over default routes, right? So they don't need any visibility into the higher layers. They don't need link states, anything funky, except, you know, the immediate link to their neighbors. One still has to deal with the reduced flooding mesh, right? So the one key ingredient was thinking through reducing the flooding mesh, and we have a fully distributed asynchronous protocol, which looks like EVPN election to a certain extent. So it's much simpler than connected dominating sets, which are normally done for generic topologies, and follow up very nicely. So it's a very easy election that guarantees that you have a redundant flooding path, but you do not the flooding storms. The topology presents another interesting problem in the sense that we cannot rely on horizontal links between at a level. That is, by most people building large fabric, highly discouraged. So we have to deal with the fact that we are operating in layers which are disconnected. Nevertheless, for the flooding reduction and for the automatic desegregation, those nodes have to be aware of each other to a certain extent. And the concept we're introducing is basically a bouncing off of the node information from a lower layer, which is sufficient to get all the job done. So the lower layers do not flood. They flood anything from what we call the south, from the bottom up, but they do not flood downwards, except they bounce off the upper layer node information. I don't want to go too deep into detail what this is necessary. You know, the algorithms precondition that when you look at the draft. The other part that we put in after having looked at, you know, like extending hellos and playing with those things was the automatic cabling detection. That is not rocket science. We basically precondition configuration of the pod. All the configuration is optional, and the precondition at which level a node is. And from there out, with a simple rule that you can only form adjacencies with people in your pod and maximum one level away, you can cable the whole thing any way you want, but you end up with a valid clause.
Do you want to move slides?
Sorry, again, yeah, the same problem. So next slide. So I'm talking about the black writing, where we form adjacencies only if we have a level difference, which is smaller or equal 1, and you are in the same pod. There are exceptions, but I don't really want to get lost in the details. So if we look at the right, we see in the blue annotation that the full topology with the prefix 2 goes up. And if you follow the reverse path, only a default route makes it down, which is basically a distance vector protocol, except that it's being done over flooding, because what we won't try to prevent is a BGP problem where if you have a lot of peers and you start to construct updates which are peer specific, which happens very quickly, but even with peer groups, you end up with serious problems scaling the implementations to support large number of peers, as I think Yandex detected. All right, I think that's it for this one, so please flip to the next one. Okay, so the 10K view, I give you an example of the automatic deaggregation, which is probably a fairly interesting aspect, and that's the last one of how the protocol is put together. Here I'm showing in the red actually 2 fabric planes, which is how, you know, a lot of people are constructing the stuff these days. And let's disregard the red, the right one. It is shown in you know, very suppressed red because it's of no interest. Let's look at the one of the fabric planes, which consists of the 2 red switches. And we see the cabling here, and let's assume that the orange link failed. So I just want to show you how the automatic desegregation is working. So prefix 1 will make it via flooding, of course, only to the bottom red switch, because otherwise there is no flooding path, right, for the P1 to flow up. So the bottom red switch has the information with the P1, while the upper red switch does not have it. Now, how does now the lower red switch know that it has to desegregate the P1? So one could do a lot of things like, you know, requesting a forever not, and, you know, remembering that you never saw the prefix, which all doesn't pan out if you look at it practically. What happens is here is that don't forget that we have the reflection of the node information from the lower layer. So the 2 switches see each other node's information, which I should define as they are aware of what adjacencies does every red switch have in this fabric plane. So the bottom switch will see that the upper switch does not have the adjacency through the green node that is the next hop to P1. So it does not have to compute an SPF for the other switch, But what it does, it computes an SPF for itself, and it looks at P1 next hops. And it realizes that the upper switch, which is in the same fabric, does not have any possible next hop to P1, which means that P1 has to be disaggregated because otherwise the upper switch will black hole it. There is simply mathematically no other possibility. The disaggregation, if you start to think through the details of it, does the minimal amount of disaggregation. It does not propagate to the lower layers because don't forget we are running a distance vector here. So the P1 shows up here while the green will be still just advertising D4 route. So the blast radius is minimal, okay? While at the same time, we are preserving the maximum amount of, of ECMP through the fabric.
Tony, please wrap up. You're around.
Yeah, okay, so that's it. Flip the next one. I'm pretty much there. So what else? I just ran through a couple of bullets that are worth mentioning. Yes, we do support traffic engineering via flooded DV overlay. So that's in the draft. We basically are capable of distributing prefixes with policies. The SPF is on this kind of protocol loop-free. So we can do non-equal ECMP. We can do weighted non-equal called ECMP. The stuff will saturate the fabric as far as you want. Like I said, we do the flooding reduction of fully automatically via simple election. And we do fairly radical deviation from how the protocol has been built so far. We will not do any handcrafted packets, densely packed binary formats. We went completely to models, which we know at this point in time we have the resources to use in terms of CPU memory and so on. So the protocol will be very extensive, very easy to extend. We can run off protobuf of Rift models. The protocol is channel agnostic, so we suggest to send the hellos of the UDP multicast. It's still the best way, while the flooding can go over quick TCP, UDP, whatever. I skipped the next one. We leave out purging. The complexity is excessive. We do have the memory today to let this thing camp. They will not introduce connectivity problems. And like I said, we have a key value store support, which is something I simply don't have time to go further in. Next one. All right. We didn't touch leaf-to-leaf. That's still open in the draft because the requirements are still kind of pending the discussion. We can do leaf-to-leaf, but you know, it's a discussion that should only be had if it's really relevant. And BMA is left out. We only have one serious party asking for it. We do parallel links. That is an interesting discussion that will be driven by laser costs and so on and so on, where the parallel links are even, hugely important. And of course, the interaction between BFD, LFA, FRR, which are all possible, but that's something to be discussed out, driven by, by interest and implementations. Next. I think that's it.
Thank you, Tony.
Thank you
so
very
you've
much.
got time for one question.
Yes.
Okay, with no questions, we'll move to the next and last presentation.
I have a quick question.
Please introduce yourself.
Okay, can we go back to that slide number 2 or? Number 3.
Yes.
Hey, Tony?
Yes, shoot.
A question for you. Are you sure you didn't cook this slide up?
What do you mean by cook this slide up? Did I do it myself? Yeah, I did it myself.
I'm just messing with you because you have all green arrows on, or rather blue arrows on all the bullet points on this new protocol, and you have all the red X's everywhere. Very much like you cooked something up.
What does mean cook something up? We can discuss those.
Yeah, let's take it offline. It's not a technical discussion. Okay.
It's Dmitry Afanasyev from Yandex. I also have a small question.
Sure.
Can you go to the slide where you showed disaggregation? Yeah, so it's half comment and half question. First, I actually like how you decide when to do disaggregation, because basically disaggregation is non-local decision and you always need some information about neighbors. But I have a question, because if you don't propagate changes beyond the leftmost green box, sometimes it's okay, but sometimes you really want to adjust load chain proportion on the leftmost blue box, and if green box can be used for some traffic, you might want to steer more traffic to the second from the left green box.
Absolutely correct. Yes, that's a very deep observation. We had a section written on that, and we threw it out of the draft because it leads to more complicated algorithm. But this is possible. You have enough information to do precisely that, which means you do non-equal cost steering depending of how much capacity you have upstream. We decided at this point at time against it, but think through that. Basically what you need on the green, very left green switch, you would need to advertise a default route with a higher cost than the next green switch, and that will achieve precisely what you want. But you need to re-advertise the default route with a different cost, which actually extends your blast radius. We wanted rather a minimum blast radius rather than trying to do like the perfect load balancing, which may change so fast in terms of utilization of the fabric. But it is a perfectly valid observation, very, very deep insight actually.
Okay,
well, thank you everybody. We'll have to stop here, otherwise it isn't out of time. Next presenter. Any questions, please send them to the list. Please keep same subject so it's easy to filter out. And next presenter, please get ready.
Hi, can you hear me? This is Bhumip. I will be presenting the FAR update on behalf of my colleagues who are in China. It's basically 3 AM in China, so they could not join. Can you hear me?
Yes, can hear you.
Okay, so this is an update from version 7 of the draft, which has been published in middle of November. Next slide, please. And send your comments to the distribution list. I may not be able to answer all of them, but please send the comments to the distribution list so my colleagues and others can see and we can resolve the discussion. So this is basically an outline of the talk. We'll talk about the background and describe briefly what fault avoidance routing is and difference from the existing one. Principles will be touch on one of the use case and of course the advantages and drawbacks and the future works. Next slide, please. So the main issue we're trying to address here is the scalability. So as you know, as you have heard from the presentations from Facebook, LinkedIn, and Yandex, this rapid development of virtualization and the cloud data center, it produces lots of demand on the scalability of the data center is growing very quickly. So, and as we have heard from the previous presentation, people are trying to adapt the existing protocols and also trying to invent some of the new ones to address these issues. And this proposal is one of such attempt to address these scalability issues. Next slide, please. So, in terms of the background, what we are trying to address is these traditional tree-like architectures and the routing protocols are not suitable for very large scale or massive large scale data centers, which we are trying to address in this session. And some of the new architectures like Factory, B-Cube, Matrix DCN, they are also currently being applied, and we also heard about the clause. And in order to maximize the benefits of the new architecture, new architectures, now the new routing methods are being proposed according to the features of these Factory, B-Cube, and topologies. Next slide, please. So what is the fault avoidance routing? It's a very simple mechanism. It's a generic routing mechanism and the framework for large-scale data center. And the protocol is designed to fully leverage the regularity of the topology of the network. So right now it works with regular topologies, and maybe in the next version when we update it, can address the irregular topologies as well. But right now it's focused on addressing the issues in regular topologies only. And it's a high performance routing method which computes the routing table in a simplistic manner. We try to keep it simple, and also some of the provisioning can be automated as well. We are working on that. So in the first half of the presentation, we heard about people want simplicity, auto provisioning, and others. So this scheme addresses most of this and complies with those requirements. Next slide, please. So the difference between the FAR and the other routing methods, including OSPF, ISF, and RIP, is that this is designed for regular topology, which means the distribution of the nodes, addressing, and the connections, which are well designed, and the node knows the whole topology without learning in a network. So other than that, the routing method for specific networks such as soft-tree BCU is generic routing and suitable for any network with a regular topology. So the keyword here is simplicity and also the regularity of the topology. Next slide, please. So the principles of the fault avoidance routing is the network devices, including routers, switches, and servers, and IP addresses based on the location, physical location, and also some of the updates can be used location virtual, so they could be physically in different places, but virtually could be together. And it's based on the two routing tables. One is the basic routing table, or BRT, which is based on the local topology, and the other is NRT, or the negative routing table, is built on the link and the device failure in the network. And the lookup to both BRT and NRT is required to determine the final route in a routing procedure. So basically, you have the BRT and you have the NRT, and then in order to determine the final routes, you find the matched routes in the BRT and subtract those matched routes in the NRT. So that's what the avoidance of the fault means. You are subtracting or you are eliminating those fault routes, and then you come up with the final routes. Next slide, please. So this is the routing of fault avoidance routing. The link state learning, the neighbor link detection. Step 1 is shown, and then step 2 is the device learning, and goes to the 3, which is the link failure inferring, and then 4 is the link failure learning, and 5 is the building the basic routing table, that's the BRT, and then based on the link failure, you have built the negative routing table, or NRT. So 5 and 6 are the routing table building, and then finally the 7 is the query for the routing table. So the routing table query produces the subtraction of the basic routing table from the negative routing table from the basic routing table to come up with the final route. That's shown in the rightmost block, which is the routing table query result. Next one, please.
Guys, please go on mute. Hey, someone's broadcasting news. Thank you.
Can I continue now?
Yes, please.
Yeah. So this use case factory network, as we are seeing, we have this port 1, port 2, port 3, and port 4, and we have the top of the rack dot 1.2, 1.1, 2.1, and 2.2, and then 10.1.01 and 10.1.21, which are related to the port 1, and then for port 3, 10.3.01 and 10.3.11. Next one. So the BRT of aggregation switch for 10.1.01 is easy to build because it's for routing according to the local topology. So if we take 10.1.0.1 as an example, so the BRT for this one, the basic routing table, will be just shown in this table. So we have the destination mask and the next hop, So 10.1.1.0, the next hop is 10.1.1.1, and for 10.1.2.0, it's 10.1.2.1. In the same way, so 10.0.0.0, the next hop is 10.0.1.1, and for the 10.0.0.0, the next hop is also 10.0.1.2. Next slide, please. So the NRT of the aggregation for 10.1.0.1 is basically determined by the link and device failure in the network. So if you assume that the link between 10.0.1.2 and 10.3.0.1 fails, the NRT for the destination is 10.3.0.0 will be the next stop, which is the 10.0.1.2. Next one, please. So the node 10.1.0.1 forward a packet to node 10.3.1.3 and calculate the candidate hops. The 10.1.0.1 looks up its basic routing table and obtains the following matched entry. So the candidate next hop is either 10.0.1.1 or 10.0.1.2. Next page, please. So the calculate, to avoid the hops 10.1.0.1, it looks at the negative routing table, so which has the following entry 10.0.1.2. So the hop to be avoiding, is 10.0.1.2. So finally, it calculates the applicable next hop from subtracting the negative routing table, which is 10.0.1.2, from the basic routing table, which includes both 10.0.1.1 and 10.0.1.2. So the final forward packets to the next hop is 10.0.1.1. Next one, please. So the advantages, it's a generic routing method and suitable for data center, but the only criteria is we focusing currently on regular topology. It's a high performance routing method which supports very large scale networks. In the draft, if you look at section 9, we have the simulation results with certain use cases, and the first switch is also simple and cheap, so it can lower the construction and operation costs for data centers. So that's one of the objectives. Next. So the drawback, as we mentioned before, it's focused on the regular topology. It does not give the universal method, and we may need to design for addressing other types of topology as well, which we will be doing in future. And now we are solving the problem. We identified the topology definition language to describe regular topology. And based on the TDL, we can design the universal method to calculate routing table for part switches. That's currently being done. Next one. So the next action is routing. This is draft has addressed the routing method based on regular topology, which has advantages for large scale next generation data centers, which needs massive scalability. No other draft in the past has addressed this problem in regular network topology in data centers. And we look forward to comments and suggestions and for adoption of this drafting group. Next one. Thank you. And if you have any question, we can, the address is here, or I know we are running out of time. So I request everyone to send the questions and comments to the distribution list so we can address this and improve this draft. Thank you very much.
Thank you for the presentation. We do have some time for questions, if there are any. Okay, then. Thank you, everybody, for joining us. Presenters, thank you so much for presenting. And
Jeff?
Yes?
Thank you.
I don't have a question on the last presentation, but are you going to have a separate list for this? I know you've been cross-copying a number of lists.
So I'll prefer to keep discussions on routing working group list. The cross-postings are not healthy,
Right. Okay, so you might want to, as a follow-up, rather than just closing the meeting, you might want to send out an email on that, what the next steps are.
Oh, absolutely.
Okay.
So I would really like to continue this discussion on list So please send your comments, questions, answers. Please react to each other questions. We'll discuss with the ADs and Chris the results and how we proceed with it. So thank you very much again, and have a great day, night, wherever you are.
Thank you. You too. Goodbye.
Bye.